some of the people who are Digitech teachers may find that they will be surprised at some of the content descriptors in the maths curriculum and the way that they cover algorithmic thinking. And Helen will be diving into that. And then I'll be looking at some of the other things in the secondary classroom as you go further with coding and algorithms in the Digitech curriculum. And then Daniela will be talking about other digital applications that aren't necessarily related to coding, but are useful for mathematics in secondary classrooms, so Geogebra and Desmos. And we'll finish with talking a little bit about spreadsheets and why we both think they're really important. So, and then there'll be some time right at the end for questions as well. So I'll hand over to Helen now so that she can get started. Thanks, Helen. Don't forget to unmute yourself.
Okay, can everyone hear me there? Thank you. Okay, and as I said, thanks, Nathan. And yeah, for those that don't know me, I'm Helen, one of the secondary education consultants, along with Daniela from the Maths Association of Victoria. One of our classroom practices, for those of you that either aren't from MAV or have not participated in MAV members have not participated in a MAV workshop before, we always like to promote the notion and role model, as we would in a classroom, the notion of always starting a lesson with a warm-up activity. So today's warm-up activity I've got for you is a Ken puzzle. And for anyone not familiar with Ken, it is basically, it's quite similar to Sudoku. However, there is actually no mathematics in Sudoku. All you're doing is literally writing numbers. So you could actually do Sudoku with letters of the alphabet, wouldn't make any difference. So with Ken, you actually have a mathematical component. So you'll notice that, and we have various forms of Ken. This is a 3 by 3. So therefore, I can only use the digits 1, 2, and 3. I can go to a 4 by 4, and if you want to get really challenging, they go up to a 9 by 9 and beyond if we do. So the way we actually have it, we have some heavily marked squares. So you'll notice there's a bold line around the 2. There is a bold around these 2 down the bottom that have the negative, the 1 with a minus in that corner. They are called cages. In the upper left-hand corner of each cage, there is a number and a mathematical operation. What that's referring to, so they've given you a hint in this one, so that number in the middle is 2. What that's referring to is the mathematical operation you must perform with those 2 numbers in these 2 little grids to get that as a solution. So in this one here that has 1 with a subtract sign, it's saying I want 2 numbers out of 1, 2, and 3 that when I subtract them, give me an answer of 1. So that can be 3 and 2, or it can be 2 and 3. The order doesn't matter. So obviously in this one, we can't place the 2 here because it's in the row. So the idea of having each digit only once in each row and only once in each column is the same as Sudoku. But unlike that, you have to also make sure that the operation. So this one's got the 2. Here we want 2 numbers that when we subtract give 1. Here we've got 2 numbers when we subtract give 2. Here we've got 2 when we divide give 2. So likewise, as I said, you can't repeat any. Might just give you a couple of minutes. You can actually type a solution. You might just want to put your 3 numbers in 3 rows. So 3 rows in the chat box. So I might give you a couple of minutes to have a look at that one.
Okay, terrific. So as I said, those that are following the Australian curriculum, there is nothing specified in the Australian curriculum as such within the mathematics component of the Australian curriculum that refers to algorithmic thinking. However, those that are following the Victorian curriculum, that was where the Victorian curriculum was different. It was actually amalgamated into the number and algebra content strand. So every level from foundation right up to 10 and 10A, there is a content descriptor that's related to algorithms and coding in mathematics, and 2 elaborations have been included in at every level, and it's within the pattern and algebra substrand of number and algebra. We do have, as I said, various approaches developing and coding algorithms can be used, and we'll go through these, and at various levels they will start from a fairly basic and even into pseudocoding, etc., and also at the higher level suggesting some programming language. So that's where the Victorian curriculum, particularly for mathematics, is a little bit different than the national. So those in the Department of Ed schools are required to go by the Victorian curriculum. So it does go, and I've got a couple of little points here. So following from foundation level, we want short sequence of instruction. When we go into level 1, we've got repetition process. We move on. So when we go into level 4, we've got some basic algorithms. We go into following some flowcharts, algorithms, and bringing in repetition. And then by the time we're moving on, I won't go through these, you'll get them as such. I do have a document with the number and algebra content strand and everything that's required within the substrand. So by the time we get to about level 8, they're also using algorithms and therefore trying to work through, and some basic programming language will come in at level 7 as well. A few definitions of what is defined as what a flowchart algorithms are in that sense before we do go further, and these were from VCAA. So we've got what an algorithm is. I won't read these out, you can see these here. So sequence, a decision, and an iteration. And I'm going to start with some really simple process, because sometimes within mathematics and depending on where we are, we've got obviously our digital learning people are more familiar with this, but some of the really basic things you can do in mathematics, even at the early secondary level, is just get kids to think about that notion of a flow chart and how they would explain something. So a flow chart will consist of those 3 different symbols. I've included some printable shapes, because what I've done with these in the past with students and also with an audience is actually laminated those and had them as pieces that they can write on and then demonstrate a particular task. So I'll run through that. So you can start with a very simple flow chart when explaining this to students. So these are your decision template. So forecast rain, and this leads to my path. No, so therefore I don't take my jacket. Yes, and I will take it. So very simple. You then can create ideas with a loop. So I'm here simulating the notion of what actually goes through when we're trying to simulate running a 100-metre race. So as the starter's gun sounded, no, then I've got to wait. Yes. So what am I actually doing? Assuming I'm moving my right leg, my left leg. Don't know if anyone goes the other way. If we've crossed the finish line, then that's it. If not, then that process just continues in that cycle. So there's our loop. As I said, one of the things I've done is actually, I've got this as an example, but when I've done this with a big group, I've had those templates available in little envelopes, laminated and available in envelopes for people, and I distribute one to each group and I get them. So I've used my example here, where you try to think through either a task or a hobby that you've got and how you would explain it using a flow chart. So I've actually gone through how would I knit a basic stitch. So I'm holding my needles with the stitches on it in my left hand and my empty needles in my right hand. I use the wool, the back of my work, and I place my right hand needle into the loop from front to back, etc. So I've explained the steps here. If it's the last stitch on the needle, then I've completed my row. If it's not, I go back to this loop and keep going. So that's one that I've used. And then what I would normally do is hand out those little laminated cards and get each table group to choose a task or a hobby. And on the back of those, actually write the steps. And yeah, that was quite interesting. So each group then walked around and had a look at how each other group has actually explained what they've done. So we've had people from making a cup of coffee. So it goes through that thinking process of what's actually required to set up the basics. Okay, I'm The other thing that we tend to do is a few little apps that will take us through. So sorry about that. The arrows have gone over my text. I should double check that when it's gone in this format. So Lightbot Hour, if those of you who aren't familiar with this one, it's a nice little free app that has a few again, ranges in levels, so it can actually go quite difficult, and it can be used with like primary age kids, but even year 7s and above can have a bit of fun with this. So again, it sort of, to me, it simulates, for those of us that can remember the old turtle logo type idea, where you sort of your commands are either moving forward, you've got a light bulb. When you go to level 2, you've got the left and the turn, the right turn, you've got your 90-degree moves, and you've got your jumps up and down as well. So a few little decisions and working through that process in a flowchart type setup. So this is what it looks like. As I said, you've got your forward, your left turn, your right turn, your jump, and then your light, and various levels in doing that. So a simple little app. And yeah, if we had time, we'd get people to download and have a go at this stage, but you could do that in your own time. All right, and finally, I've just got a few of the apps. I've got Lightbot, the KenKen app. I talked about KenKen, that's there. The Lightbot Hour, as I said, programming little puzzle, and it does require that basic logic to really encourage that. And these are some of our other favourite ones that we like to use that also demonstrate some mathematical, they have some maths behind it. So those of you who like pentominoes, Pentomine is a great little app that works with pentominoes. There's a geometry one here, Tangram Kid. So again, if you're doing tangrams, it's an application of tangram, and then another geometric one as well. So that's my little section. And if there are any questions, I'm going to stop sharing. And yep. Terrific. So as I hand over to Nathan's going to share, and if there are any questions in between, happy to take any questions there.
Please feel free to put any questions into the chat if you like. You can do that while we're talking as well, and we'll get around to answering them if we don't answer them.
Okay, over to Nathan.
All right. Hopefully everyone's seeing the screen there. Those of you who might be new or not sure about the digital technologies curriculum, just briefly, it is a learning area that's part of the Australian curriculum and part of the Victorian curriculum. In secondary schools, it's often taught by a specialist teacher, or often it's a maths teacher, or it might be a teacher of another subject, or someone who's come in. The connection point that I wanted to make today with what Helen's been sharing, algorithms in the Digitech curriculum are part of what we call computational thinking. And in that way of thinking, there are sort of 4 steps that you do called decomposition, pattern recognition, abstraction, and algorithm design. Just quickly defining those, decomposition is this idea of breaking down a complex problem or a system into smaller, more manageable parts. So trying to figure out what are the bits and pieces of this problem that I'm trying to solve. Sorry, these numbers haven't gone through. Second one, pattern recognition, looking for recurring themes and similarities that can lead to predictions or shortcuts in your code. Third one, abstraction. This is an interesting one. This is where you generalize, you look for important information, you ignore irrelevant details. You don't need to put everything into your program, you put in the things that matter to make it work. And then algorithm design, where you develop your actual solution by step, so that a computer could carry out the instructions to solve it. In the Victorian curriculum, these algorithms are generally captured in the strand in the Digitech curriculum called Creating Digital Solutions. And I've put 2 examples there from levels 7 and 8. One of them is to design algorithms represented diagrammatically and in English, and trace the algorithms to predict output for a given input to identify errors. Now, there's a lot of vocabulary in these, as you can imagine, and we're not going to explain all of that vocabulary today, but I do want to highlight a few things as we go through. The other one is to develop and modify programs with user interfaces involving certain coding techniques, branching, iteration, functions, and using a general purpose programming language, which we'll talk about. So, what can this mean in the secondary classroom? So Helen talked about flowcharts. In Digitech, by the secondary years, we want to be introducing what they mentioned there in English, or in the United States, in structured English. And this is often with something called pseudocode. Pseudocode, as you can imagine, means false code. It's kind of like a sort of a universal type of code that most people can read, but it's not quite the same as Python. It's not quite the same as JavaScript. It's something that you use to explain your algorithms. So it's a little bit more loose than an actual programming language. So you can see on the left here, there's a simple flowchart for a little algorithm. And on the right, that's been converted into pseudocode. So it's the next step before actual code. Another thing that was mentioned in those content descriptors was tracing. The idea of stepping through your code at the design stage and see if you can predict what it will do. So that might happen while you're coding, but it can also happen when you've got your code written on paper or in pseudocode. You can manually step through and try to predict what it will do. And the other big thing that happens in secondary in the Digitech curriculum is we're moving from visual coding, so something like Scratch you might have heard of, or one of those blocky languages, as you can see on the left, and moving to what we call a general purpose programming language, which is something like Python or JavaScript. The other thing that happens is we start to bring in more complex structures in code. Things like functions, which allow you to organize your code and generalize the functionality, and things like arrays, which are a data structure for sort of organizing data within a program. So like an array is often called a list. Instead of just one number, it's a list of numbers, or a list of other objects or data types. I've got a couple of examples here of things that you might do in a maths classroom or in a secondary maths classroom. Some of these could still be done in a visual coding environment like Scratch, and some of them lend themselves more to a general purpose programming environment like Python or JavaScript. So some of the simplest things you can do is just converters. Write a program that converts a value from Fahrenheit to Celsius, or converts between different currencies. Hailstone numbers, the collapse conjecture, is a really interesting one for the maths teachers. So hailstone numbers work by a fairly simple little algorithm so that you get this sequence of numbers. And what we note is that if you apply this to each number, to the next one, to the next one, they seem to come to the number 1, no matter what number you start with. The question is, and the conjecture is, do they always get back to 1? And we can do the first sort of shorter sequences by hand, but that's what computers are great for, is if we can code in an algorithm to perform that, we could try much, much higher numbers and see if they still come back to 1. We may not be able to solve the conjecture, but we can certainly explore it a lot more. Another one that I'm just going to quickly go through here is a number guessing game. And I wanted to just show this one as an example of how you might apply this computational thinking. So you make notes, you do your flowchart or your pseudocode, and then you do your code. So we're going to do this game where it's a guessing game. The user, the person using the program, is going to think of a number, and the computer is going to take a guess. Then the user will say lower or higher, and then the computer will keep guessing until it gets the right number. Now, if we were solving this problem, we might think to ourselves, all right, what does the computer need to keep in memory? What does the computer need to know? What are the things it needs to remember? And if you play this game with someone else, your first guess would probably be 50, right? You'd probably guess somewhere in the middle, and you'd be doing what's called a binary search. You'd be constantly guessing in the middle. So you might guess 50, and then if the person said, oh, go lower, your next guess might be 25. So what's actually happening there? Let's break that down. Well, you're remembering, you're bound at the start, you're remembering that it's between 1 and 100. And then if they said lower, now you're remembering it's 1 and 50, and so on. So if we look at how the pseudocode works, we might start by saying, think of a number, and we've got these two boundary variables that we have to remember. The bottom, we're going to start as 0, not 1, and the top, we're going to start as 100. And then we've got a loop or an iteration. And this loop is going to go forever. In this case, I've simplified the program a bit. And our guess is going to be the average of bottom and top. It's going to be halfway between them. And then we're going to say, is it this number? Now, the user then gets to respond and say, no, it's lower or higher. So the user types in their response, and the algorithm says, well, if the user said it was lower, what happens? We reassign the top. Now the top is 50, or guess. Or if they said higher, then we reassign the bottom. And the algorithm then repeats and repeats until the user can confirm that the computer was able to find the right number. Now, if you were to actually do that algorithm in code, you might get something like this. This is a Python example, and it's a little bit more complicated because when you actually do your code, you might realize, oh, I'm getting like decimal numbers, I'm getting 0.5s and things like that. So you have to put in a little bit of extra work so that you can sort of round those numbers down and make sure you're getting the right thing. A couple other examples, I'm not going to actually show these, but Helen also mentioned earlier about the turtle. The turtle is still very much a real thing in education and coding. It's in Scratch. It's also, you can do it with Python. But the turtle, where you're navigating it around, drawing regular polygons and writing functions so that you can draw any regular polygon, those sorts of things are a great thing to connect to maths. The other big area is with data, using code to actually analyze data. And later on, we'll talk about spreadsheets. But you can also write Python programs that can bring in a data file, whether it's text or numbers, and write programs to work with that data. The link I've given you guys there at the bottom, we will, as we said, everyone will get the slideshow at a later date, but that link takes you to a sort of a sheet with a bunch of links to other maths-related Digitech resources too. I think that might be the end of my section, yet. So I'll, if anyone has any questions, I'll just turn this off and then we can hand over to Daniela.
Okay, please feel free to unmute yourself and ask any questions at the moment, or use the chat facility.
Okay, hi everyone, Daniela here. What I'm going to do is I'm going to steer a bit away from the code and algorithmic thinking component. And I'm going to share a few of my favorite digital technologies that I've used in the mathematics classroom quite a bit, that I find underutilized and very, very effective. And I want to show you just two of those today. And they're both quite similar. They're actually competitors in the industry, and I find they're both wonderful. So either way that you go is perfectly fine. And you might use one for some things and one for something else. Okay, so the two I'm going to show are Geogebra and Desmos. We'll start with Geogebra. Geogebra is fantastic, and one of the reasons it's fantastic is because it's free and readily available. So you simply go to geogebra.org and you've got it there. Now you can use it as a website kind of browser application, or you can actually download the software, have it on your computer, and create files in that as such. It's great for algebra, geometry, graphing, calculus, spreadsheets, statistics, anything, really anything that in mathematics you can think of, Geogebra can do. It even has CAS functionality now as well. It's great kind of introduction to CAS computing, so a great stepping stone for students who might want a bit of an introduction to that kind of technology before they use their Casio or TI Inspire calculators later on in year 10, 11, 12. It's really a really simple and easy to use interface, and it's really dynamic and interactive, which appeals to students. Okay. Going to go to the next slide. Now there's three ways you can use Geogebra, and I'm going to demonstrate a bit of all those three ways. The first way you can use it it's for absolute beginners who don't have to have many skills at all in terms of using Geogebra, is just to simply find pre-prepared applets that someone else has created and to model concepts. So what's wonderful about Geogebra is it's got a huge library of resources, a huge bank, and I'm just going to change my screen over now to show you that. 1 second. I'm going to stop sharing this and I'm going to start sharing my computer screen. 1 second. So hopefully you'll see that now. Can I get a thumbs up, Nathan or Helen, if you can see the Geogebra screen? Yep. Wonderful. Okay, so here I am on geogebra.org and you can sign in, you can create your own username, and then there's a whole search function here, so you can search for anything you'd like to demonstrate, a concept you'd like to demonstrate in class. So for example, if I want to demonstrate volume of prisms, oh, there you go, I've already typed it in. Maybe in preparation for this, you never know. Okay, let's have a look. So I type volume of prisms and I get a whole bunch of resources other people have created. And I can just then go and find one that demonstrates a concept I want to teach in class. So for instance, I might choose this one because it looks fancy. And if you have a look at this one, it's actually a whole pre-created worksheet for students. So the students can interact with this applet, it's called an applet, by changing the number of cubes in the first layer. So they can drag the slider across here, change the number of cubes in the first layer, in the second layer, and number of layers, so that goes up in height. This can simply change the way that the amount of opacity in the colors, so they can change how much it's filled. So it's a very simple applet that starts getting students thinking about the notion of volume and getting them to understand what a cubic unit looks like from a conceptual point of view. And then they have a series of questions to answer down below here. All right, so I'm just going to go back and show you other things that I've used it for. So this is, like I said, simply if you just want to use Geogebra to demonstrate concepts and not actually create any of your own things. I've often used it to demonstrate the unit circle. Gone are the day, I think, where teachers have to try to draw freehand circles on the whiteboard, and so many of them, and you never quite get it right. And if you do, students are like, how can you draw that so well, miss? You know, but so these days you've got wonderful applets like this, and you just project it hopefully on a board and that you have it, and you can interact with it like so, and the concepts of what cosine, etc., become very, very clear to students. Talk this through. Now I've just selected one at random. I can go back and show you that there's hundreds of unit circle applets people have created. Just going to find another one. So here I've got another one that I'm going to show you. This one, you can select which functions, so sine, cos, or tan, that you want to demonstrate. So let's go cos, for example, cosine, and you can change the size of the angle, and it's demonstrating the cosine value and at the same time simultaneously plotting the trigonometric function for you. So you can really slow it down and explain what's happening to students, and they can get a better conceptual idea. Okay, I'm going to go back to my PowerPoint now, see if it works. There we go. And the next way that you could use Geogebra is to create your own worksheets. Now, this takes a little bit more skill. It's for those people who love technology and who also are a little bit into coding, because Geogebra has its own code, its own programming language, so to speak. So you can actually program little questions in the back end, make little worksheets up that give students instant feedback about whether they have answered a question correctly or not. So I'm going to quickly show you how to do that. Second, I might just exit this and open up a Geogebra file. That I created earlier. Sorry, I'm just having a quick look for it. I'm going to start with quadratic transformations. So hopefully everyone can see this. Thumbs up, Nathan, Helen, if you can. All right, wonderful. So here's a worksheet that I've pre-programmed. Now, this is running in the downloaded software, and I'm going to get rid of some of these views because they're distracting. You can just change the views, so you can get rid of the algebra on the side. And it's got 2 problems. So I can select problem 1, and basically what students have to do is change this original quadratic function so that it kind of maps or it overlaps this one, and they have to find what the equation would look like. So they can play with these sliders and get it to go exactly over the top of problem 1. And then they can tell me that the equation for that function is -2 x minus 3 all squared plus 4. That's an example of a pre-prepared sheet that students can interact with. Another one I would like to quickly show is also unit circle one. So we've done unit circles. I've showed you unit circle ones before, but this one has a little bit more complexity. I'm just going to get rid of some of these views so that they don't confuse you. Okay. All right, so here we've got the unit circle again, showing the angle 40 degrees, and we've got the cosine, sine, tangent displayed in yellow, and then we've got a question pre-programmed into this worksheet, Geogebra worksheet. And the students have to fill in an answer here, and depending on what they say, if they say 32 degrees, they get an instant feedback that they're wrong, and they have to try again. So for example, they're looking for the equivalent value that gives us the same cosine as the current angle, 40 degrees. So that's 320 degrees, and it's correct. And what I can do is I can change my angle. 1 second, and then that 320 is not right anymore. So this takes a little bit of, like I said, coding, because this field has to be pre-programmed so that the coding page, the GeoGebra page knows if it's right or wrong, the input is right or wrong. So there's a little bit more complexity there if you're an advanced user. Another way that you could, another thing that you can use GeoGebra for is to get students to actually create their own applets. So whether it's a simple thing like, actually I'll open it again. Whether it's a simple thing like sketching their own equations. So let's say y equals x to the power of 2 minus 2, and they might do another, or maybe a linear equation, y equals half x, and they can go ahead and change the colors of those. Whoops, I just deleted it. Great. Settings, we can easily change the color of each line, like so, and you can play around with that. Now you can also do something which is create your own sliders really easily in GeoGebra. So I can put in y equals ax to the power of 2. And because I gave it a coefficient of a, GeoGebra recognizes a as a slider that we can then manipulate like so. So students can really get a set of quadratic equations really nice. And I wish this kind of existed when I was a student, because I would have been super excited by it. You can then play around with the functionality on the top here, putting points on objects, putting points on intersects between different lines, etc. And then students can analyze where those lines intersect. And so there's the potentials are limitless, really. I've also shared, if I go back to my PowerPoint, I've also shared some resources that I've created. Sorry, someone's speaking, so if I can get you to mute your microphone, please. Okay, so I've just shared some resources in this bit.ly link down the bottom, which are the ones I've created. which are, there's 4 worksheets you can use straight away in your classroom with your students involving GeoGebra. Okay, so I'm just going to go to Desmos now. Desmos is also a really interactive and freely available digital resource, highly engaging. Sorry, Helen, if you can just mute first.
Yeah, I'm trying to this.
But you guys domestic travel.
Okay. And what's wonderful about Desmos is a teacher can pre-select an activity and assign a class code to that activity. Students can use that class code to log on into the activity, and the teacher can, through the dashboard, monitor progress, student progress, where they're up to in that activity, how they're going. I'm just going to quickly do that as well. So hopefully you can all see that. This is the Desmos, Teacher Desmos platform. Now, here in Desmos, we can search for an activity. I'm just going to go to most popular. We can search for activities that have been created. You can search by topic or something like that. I'm going to choose this one called Turtle Time Trials. Now, if we had more time today, what I'd do is I can create a class code here. This green button lets me create a class code. Oops, I'll just sign in. Create a class code. 1 second. There's my class code. Now, the students log in. That class code. 1 second. We can just mute all, maybe, Helen, and then I'll just unmute myself.
Yeah, that's the only way, because there is no one that's not currently muted, apart from you and me. I might have to go back.
What
does it say about inside?
Yeah, just mute all, Helen, and then I'll unmute myself.
Go back here.
Sounds like she's very motivated by food.
Sounds like it's just another version of Coco. I think should we get it?
Sorry, everyone. Technical difficulties.
We just want to see who is.
Just mute all, Helen. That's fine.
Yeah, I know. No, it's been ungrayscaled. I can't.
I don't
Okay.
think we'll get it though.
Everyone's okay.
It's strange because we can still hear the
It's
person.
mute all, I know, and yet they're all muted.
Hello. Okay, I think that's better.
Okay.
I can still hear some mumbling. Let's just fingers crossed. Okay. Some class code is generated. Students can use that class code to log in and participate in the activity. I'll quickly show you what this activity looks like. This is a student preview. Press play to watch the short animation and write a story about what you see. And then the student might answer that. Then here we've got an additional, so in the next step. So turtles' distances at various times. So we've got that. And they can answer different questions. So it keeps progressing in difficulty. Students get asked questions and they're able to proceed, and teacher is able to monitor that on the dashboard. If we had some time today, I'd get you all to log in with that student code and answer those activities, so I can show you what I see in terms of from the teacher's perspective. This one is also quite nice, and I'll show you here. So often I have difficulty, especially the maths physics teacher, just explaining the concept of distance time graph, velocity time graphs, etc. This one allows a student to see, sketch a distance time graph, any kind of distance time graph, say, and then they get to play their own distance time graph and see what that turtle's doing if it follows the graph that they drew. Really, really nifty. I wish I knew about this when I was a physics and maths teacher. Would have saved me a lot of drawing, a lot of whiteboard marker ink, and a lot of frustration, I guess. And then what you find is students are really engaged. then, like I said, every page of an activity increases in complexity. They're refining that skill, learning how to express their mathematical language better, and are starting to relate concepts. And you as a teacher, it gives you teacher moves or teacher notes down the bottom. And so you're really guided as a teacher about how to go around in your classroom and maybe ask prompting questions. And you as a teacher can view everything. If I create a class code here, you can view everything on a dashboard. So you can see exactly which students up to what page, exactly what students answered what, etc. I think I've gone a bit over time. Sorry to my fellow co-presenters, but we did have some technical difficulties there. And I am really passionate about this. So it kind of, it needs longer to see if you can fully appreciate the power of these two wonderful pieces of technology. So I might just share the next screen, and Nathan, if to unmute as well.
Yeah, we thought we'd just both Daniela and I and Helen wanted to do a little quick thing about spreadsheets and the way that you know, these can be used so well in classrooms. And one of the main points we wanted to make is that with spreadsheets, we feel that we really need to go beyond, particularly in secondary years, the very basics of just doing data entry and a chart, but start to use some of the formulas or formulae that come in to Excel or Google Sheets or even Numbers, which is the iOS one. You've got your formulae for maths operations, but you've also got formulae for doing conditional logic. So there are formulae to add numbers, but only if they contain this type of value, or formulae to, you can even do loops. So you can start to bring in, essentially spreadsheets can bring in coding to some extent. It's not always the most pretty way to do it, but you can actually start doing coding. You can, it even goes as far as if you're using Google Sheets or Microsoft Suite, there is scripting you can even add, which is very similar to JavaScript. And you can start doing scripting as well if you want to take it that far. Another example, I don't think we'll have time to do the example, but you can also do probability experiments. So you can use spreadsheets to give you random numbers. And then because it's a spreadsheet, you can drag it all the way down and you can have 1,000 of them in the same time it takes you to have one. So these sorts of things are what it's perfect for. Danielle, did you want to add anything to that?
No, but I just want to emphasize the last point there about it being a really, really useful life skill. And I've sat in other PD sessions before of people promoting spreadsheet use, and they say that students, even though they're getting more tech savvy in general, they're less and less capable of using spreadsheets than they ever were before. And that could be because they're distracted by other more fancy technology, and that spreadsheets aren't as appealing. But in reality, spreadsheets is something that we use almost in every industry, in every job that you'll ever get. You'll find a use for spreadsheets, whether it be for budgeting or, like we said, they're making big decisions, organizing things. I use spreadsheets on a daily basis at work. Helen knows I'm a bit of a Excel lover. Yeah, so it's just so important, and we're seeing less and less capability with students of spreadsheets. And like Nathan said, if they do know how to use it, they know how to enter a list of data, maybe bivariate if we're lucky, you know, and they can then graph that. But where is that next level of complexity where they're starting to use complex functions or, you know, if statements and things like that? I'd love to see students experimenting a little bit more in that area.
And as both Nathan and Danielle have said, there's so much you could do, and I've got some of those examples there, and I've done great little activity with year 8s in maths where we've actually just simulated a spinner with the colours, and whether it's a 4 or 6 coloured spinner, and the kids really just love that, and there's so much they could get, you know, so many different long, you know, great for long run probability as well as for other things. So
it's amazing, Helen, isn't it, when see that Excel can do all these things, they're blown away because they haven't been exposed to it. I would also like if you share in chat. I mean, most people have some experience with spreadsheets and Excel. If you've got any of these kind of anecdotes and you'd like to share, please go ahead and use the chat box.
Yeah.
Okay.
I think we might skip the next slide. I was going to do a hands-on example, but we'll make sure the link is in there for the next time. We might skip over that now.
Yep, John said that it's great for VCal numeracy. Yep, it is for all those, because within the VCal numeracy you could do your business, your basic one with just your some of your just set up. But as you said, if you're doing any of your, it really would cover all areas of that. So yep, agreed.
What is a good resource for teachers to learn how to use spreadsheets for maths? Good question, actually.
Yeah, there's not in that regard.
There's not one specific resource. I think if you would like some more guidance, you can always ask or DLTV, I guess, to specifically run webinars on them. Yep. That would be something that you could do.
Yep.
So we're happy to do that.
Yeah, so please let us know. And also, if you put in specifically, like if you want to have a look at something, want us to prepare something on, VCal specifically, or on how you could use it for coding, or some of the examples we've actually set of setting up formulas, etc. Yep.
I'm just seeing a couple other comments here. Martika says YouTube clips. Yeah, with Office type applications, there's just so much out there. Sometimes it can be hard to sort out good ones from bad ones.
What's good, yeah, that's right.
But there's a lot out there. I like Daniel's comment too about using it for data and statistics, and your what's it called?
Your
five-figure summary, that sort of thing. I was going to say too, you can also, what was I saying? Yeah, you can also use, you can use Excel to, or spreadsheets to bring up sort of dynamic things as well. So they've gotten a little bit next step. So the latest Office 365, and I think the latest Google Sheets has some of these capabilities too, but you can do dynamic things where the chart changes if you adjust a setting, or if you change the, click a button, and you can make kind of your data visualizations can be a little bit more interactive, which is really cool as well.
Yeah. The one way I engage my students with Excel is quite like incidental. I didn't even mean to, but because I love Excel, I sorted out all my data on Excel that I can enter student results, and it computes, progress and growth, and, all these kind of statistical analysis. And they found it so exciting when they could see, color-coded information about their own progress in mathematics. They'd be like, "How do you do that, Ms. Draskovic?" And then I'd go and show them that way through my own passion. Then they get hooked as well. So, okay, I might just skip ahead on the slides. There's a final thought that I might be a nice TEDx video for you to watch. Helen's putting there.
It's a great little one. So have a look at that. It's a woman who is it's a Melbourne-based one, and who's an IT person, but also has a passion for knitting. So really interesting to show the coding aspects of things, and it's quite funny too. I think so anyway.
I love the name. Granny was brilliant. Okay.
Yeah.